Thank you. It's very good to be here. There's been a lot of talk over the past few years about autonomous cars. Well, I love planes, and I would argue that to some extent it's easier to automate planes than it is cars because you don't have animals and people running out into the road in front of you. And there is, at least for manned aircraft, a fairly rigorous training process that includes bookwork and exams that are practical and theoretical. So that's kind of setting the stage for big sky, not yet so many planes, and training that makes aviation very safe. That said, it's a rare person who has been in the aviation community for a long time that doesn't know someone who died in aviation. In my case, my flight instructor died about a year after I learned to fly, and 3 of the 4 planes that I trained in were crashed within 2 or 3 years. So to some extent, that motivated my desire to study aviation safety and solve problems, whether it involved people or technology. Now, why don't we fear flying on planes? Well, I slept very nicely coming out here from Detroit Airport. It's because we have a really rigorous process. We have triple redundancy, 3 of everything. We have 2 crew members, and we have a long record of training and basically making it as safe as possible, even though these vehicles go very fast. So it's not scary, but yet when something happens, it's a big deal because there are so many people on board, and if there's a crash in an urban area, it can involve a lot of others as well. So in this grand scheme of autonomy, safety, vehicles, whether they're air, ground, or other, that we want to have be better in the future, what kind of research problems are there and how do we address them, and then how do we transition that technology effectively? I'm not a big fan of pushing technology if people don't want it. But I am a fan of research, and I'm also a fan of safety. And I think there are a lot of questions related to autonomy that involve push versus pull of the technology. So I like to survey groups. You're an awake audience, so let me ask you the following questions. If today a major car company that had showrooms for many years opened a new kind of sub-showroom that had a car with no steering wheel that was autonomous, certified, safe, and you could buy it right now, would you go into that showroom? Or would you go to the traditional showroom that had the flashy new car that got the same gas mileage or electric power mileage? Which one would you go to? Would you go to the one that had the autonomous car with no steering wheel or the regular one? How many of you would go to the autonomous showroom? Oh, what's that? Well, okay, so there's 2 sets of questions here. One is, if you're curious, you'd go look. But let me ask the question a little more carefully. How many of you would seriously consider purchasing an autonomous car that didn't have a steering wheel but was certified safe? Yeah, let's say the costs are compatible because I'm cheap too. Okay, so how many of you, same cost, same certification, would not seriously consider buying an autonomous car with no steering wheel? Right, so how many of you abstain? And if you didn't raise your hand yet, then there's a problem. You're asleep. All right. What's that? Okay, so the last category, how many of you don't want to buy cars ever again? Okay, so that captures some of you. All right, fine. Well, the reason I go straight for the no steering wheel case is that I think that we psychologically feel happy if we have a steering wheel in front of us, whether it actually is being listened to by the software or not. Oh, so this is awesome, right? See that off-nominal conditions? Right, that's exactly the challenge of the automation, is to deal with the cases that you had not hard-coded and verified and validated in advance. That's really the thing that has been keeping us for many years in aviation from taking the people out of the cockpits of the commercial transport aircraft. Now, that said, we have a question to ask. What is it that we need to do? So let me take you back, since many of you are not in aviation, and talk briefly about how we got to where we are today. Well, Maybe if you're from Europe or South America, you don't believe the Wright brothers flew first, but there it is. I'm from the US. Here you go. So we've gone from having really dangerous planes that barely flew. That would be the Wright Flyer, really hard to fly, couldn't go very far, to fast and cool airplanes that now are either in museums or that fly occasionally and sometimes get into trouble. This is actually a drone. So a lot of people are like, where does the word drone come from? And if you look in the dictionary, it says male stingless bee, but the reality is the military had drones as target practice a long time ago, and people on the ground with their giant boxes with vacuum tubes in them sent signals to them way long time ago so that when pilots did target practice, they didn't actually shoot down manned aircraft. And so now our drones tend to look like that. And I assure you that's bigger than that, even though the pictures are the same size. But we've now gotten to the point where we have commercial transport flight management systems, or FMS, that are fly-by-wire and triple redundancy. So what does it mean to have fly-by-wire? What it means is that, yeah, I do want to ask questions. I'm a professor, right? I love it when people answer questions that I ask. So what it means to have fly-by-wire is that there is software between the pilot and the controls of the aircraft. A lot of people are like, oh, well, the reason we can't automate planes is cybersecurity. Well, it's too late. And we're not going back because the weight, cost savings, and even the safety have been improved by going to a fly-by-wire system that has a computer between the person and the controls. So what does that mean? That means that we have to deal with security today. And then the next question is, what kind of decision-making collaboration is best between a crew and software? So that's where we begin to ask the hard questions with respect to off-nominal conditions. The other thing, which is a note at the bottom here, but plays, I think, a larger factor than many may realize, are these unmanned aircraft systems. Right now, we have a voice-based air traffic control system. Well, do we really want to put natural language processing in the loop between an autonomous unmanned aircraft and a safety-critical instruction? I don't think so. But how do we get past that? Because the legacy planes are not even required to have instrumentation, and it's certainly not Datalink. So we have a big question there in how we get all of these vehicles to share the sky. The answer is not to have someone on the ground that's dissociated, that's not sharing the fate of a small unmanned aircraft, to be in the loop for voice communication. The answer is to actually have data link that's redundant, perhaps backups that are from different network sources, to allow this data exchange to be very fast and accurate with a sufficiently low probability of cyber attack or breach that it's safer than voice, which is known to be unreliable, especially if there is noise on the radio or there is someone who is not a native English speaker. All right, so autonomy plus flight. Again, this is not a slide that's looking at pushing autonomy because I'm a technologist. It's a slide that's looking at how it could help. So right now, it's the case that in passenger transport, which is the vast majority of what we interact with on day-to-day, how many of us got here, the flight management systems assist the pilots, and the passengers tend to trust the pilots more than the autonomy. That's the design. That's how people feel safe. The reality is many of the people in this room probably would not fly in an automated airplane any more than you go to the showroom and buy a car that didn't have a steering wheel. Well, is that because of safety or is it because there's comfort? What's that?
It's new. Something new. Nobody tried it.
It's new. So then the question that people begin to ask is, how do we verify that this is going to work well? Well, it's not going to be verified if we don't let the unmanned aircraft into the skies, right? We have to let them up there, and then they can show how well they're going to work without having people on board that might be placed at risk if some kind of interaction happened that we hadn't predicted in our validation verification efforts. Nonetheless, cargo is the next thing, right? We don't have to have comfort there. We just want to have packages or payloads for science or surveillance taken up. So when you have in your mind there, you should be thinking FedEx, UPS, all of the other large carriers that don't really want to have logistics of crew transport, as well as the small kind of toys, like the CNN quadcopter, that eventually have to become more robust. They're not triply redundant. In fact, they're barely not toys. But we have to reconcile where they go and how they operate so that we have an integrated system. Right. There's a lot of talk that even in military, the next generation fighter may be manned or it may be unmanned. That's a different conversation because that's not talking about autonomy, that's talking about weapons and their management. So I don't want to speak any more about that today. So I'll mainly look at the civil applications. So I wanted to show the picture of the Cessna that looks much like what I've flown. In general aviation, we don't want to take away our fun. We want to be able to fly. And what that means is that whatever devices are carried on board have to be reasonably priced, and they have to offer pilots the ability to have fun. That's challenging if we think about automating everything, including collision avoidance, Datalink, and so on. But it's something that factors into the problem. For civil unmanned aircraft systems, or UAS, we have two different classes. One, is the high-altitude persistent flight. These would be like the internet, solar energy harvesting, efficient power gliders, blimps, and then they also include the low altitude, so there with the let me go back. High-altitude persistent flight, it's this cartoon, or actually a real plane. I'm going to get in trouble when this is played back. You have to have autonomy. There's not going to be, if it stays up for a year or 5 years, somebody sitting on the ground watching a screen. You could have that, but it wouldn't be cost effective, especially if you had a fleet of them. And furthermore, they're doing something that's a fairly simple task. They just have to pay attention to winds, weather, energy management, and then the data that they're collecting and disseminating. In the case of the small UAS, whether it's for delivery, inspection, rural, urban area, there's two classes of vehicles. One, I'll call low integrity UAS. This is what has flown for many years. Line of sight, or LOS, low altitude, keep it above a property and it's okay. Well, that's what came out of the hobbyist or model aircraft community, and that's what's still safe. Where we're becoming confused now is that now we're thinking of flying over urban areas and at altitudes that interfere with manned aircraft. And it just is a different class of vehicle that needs to go there, which I'll call high integrity UAS. If you don't have redundancy, if you don't have onboard decision making that's a little more clever than ditching into a crowd at a football game, then you're going to be in trouble and it's going to be unsafe. So to some extent, the industry and the regulators need to recognize these two classes of vehicles and handle them. That's not just a technology question, that's also a policy and industry question. All right, so what is autonomy? If you look in the dictionary, it says the quality or state of being self-governing. Robustness is important. Autonomy must be robust to complexity, uncertainty, and risk potential. So you have this system that you should retrieve, process knowledge, and then use it in decisions and learn if possible. This is a general slide. So some of the challenges then are handling rare or unmodeled events. How does a decision-making tool react if it has some kind of stochastic model of what to expect and then something rare has happened? Furthermore, what if it was not modeled, whatever event it was? Then one can only see data that's observable and then try to understand how to react. The environment, the mission itself, the platform, all of those could change over time. And then there's the matter of safety and trust and using the Internet of Things, which is, I guess, a big topic here. All right, so here is a slide that I like to show because it kind of puts in your mind what we face. On the left are really good pilot behaviors, even though you see planes in non-traditional locations. These are good pilot behaviors where they were dealing with somewhat unexpected events and made good decisions. In the top one, that's solely in the U.S. Airways plane in New York. On the bottom left is a plane, general aviation, where the pilot had an engine failure and ended up landing on the Cross Bronx Expressway in New York in an area of construction, and nobody died, nobody was hurt. On the right, I think the top one explains itself. The one in the middle is a curious case of a drone flying into the White House, which spurred a whole series of developments in what's called geofencing. I'll talk about that in a minute. And then the one at the bottom was the German wings flight. The one thing I want to point out here, which is kind of morbid but necessary to think about, we know how to stop that in autonomy, right? If you have a working airplane, why let it fly into a building? Right? That's a big deal. Every Boeing and Airbus plane flying today will still allow that to happen. That's wrong. That's an example that happened well later. So what can we do? Well, from a technology perspective, there are several different avenues to pursue, not just to develop the autonomy mathematically, but then to show how it fits into an overall system that can take us from existing flight management systems that rely on pilot inputs to a system of checks and balances that can benefit from pilot inputs, but then also can make even the highest level decisions to keep a vehicle safe or where it belongs. So I'm going to talk in the remaining minutes about 3 specific research projects that my group has worked on at the University of Michigan. The first one, geofencing for small UAS. The idea of that is to prevent flyaway from test sites that you're cleared to be at, or to prevent the vehicle from going into an area that it's not authorized to be in. The second one is emergency flight planning. What happens when something goes wrong? If you're in a car, the goal is to pull to the side of the road. We only wish for that in aviation. What we have instead is a plane that is in the sky that we really wish were stopped on the ground. But you can't just fall from the sky, especially in a manned aircraft, because that would be catastrophic. So there's a whole series of activities in flight planning, understanding the dynamics and what the range of possible commands is. That would be the flight envelope. Understanding how a controller should work, and then following that flight plan all the way through landing, despite the potential for the damage or failure to get worse. This third thing is what I'll call envelope-aware flight management. This is a hard problem for any autonomous system. When can the software take over from a human or nominal automation? That's the question that is right in front of us for the cars, the planes, and everything else that is going to be a shared system where we have decision-making potential by both the human and the autonomy. So this is our work to look at that question for aviation, specifically for cases of loss of control, or LOC. All right, so obviously I have to be very quick. This is 3 kind of substantial research projects, and I have a couple of slides on each one just to kind of give you a little more information about where we've been going in these tasks. I'm happy to share publications or other information with you after this talk is over. So geofencing, there's 2 versions of it, and they have different names depending on who you ask. Keep in and keep out. Keep in means that you don't depart a cleared test range. Keep out means that you don't go where you're not supposed to be. So how do you specify that? Well, you're going to say what the ceiling or floor is, that bounds altitude, and then you're also going to say what type of boundaries you have. Now, one of the connections, which is really important to the kind of Internet of Things community here, is right now all of the systems have user-specified coordinates. That produces a data entry error potential or misuse. What you really want to have is something that's data-driven. Now, some of the companies have kind of things like White House lawn and stadiums cut out right now, so DJI won't turn on your system if you fly it near the White House, for example. However, those are static, pre-programmed fence boundaries that would not certainly satisfy the keep-in dynamic boundary kind of system for each plane. A better system and I hope to talk to some of you during the day today about this, is to actually use other data like property maps. What do you own? Who owns the plane? Who owns the property? How do you get permission based on that? That's one of many data sources. Obviously, the clearance to fly in the airspace is another. So how does it work then? Well, you monitor the location. You either keep out of boundaries or keep into them. You have, ideally, an independent system, this thing in green, that would be watching for a violation and then correcting to cause the violation not to happen. We have 3 modes. We're focusing on the guidance problem. Other people, such as groups at NASA, have been focusing on the control problem. In the guidance problem, we have 3 modes. One is shared control, another is return to launch, and a third is local loiter. With shared control, you're basically bouncing off the wall and not leaving the area that you're supposed to be in or not entering the keep out area. With return to launch or an updated location, you're driving back to a waypoint. One of the things that's a little bit hard there is, especially if you're at low altitude, you need to not just go in a straight line. You need to avoid obstacles and other hazards. And then local loiter is a variation of return to launch where you hang out but don't follow the user's commands until they're made aware of the problem. Right, so next, emergency flight planning. And this is going to be really fast. Actually, I'm going to give you a 1-minute emergency flight planning discussion and then 4 minutes on the other. So this slide is from about 15 years ago, where we first started looking at how do you do emergency flight planning with commercial transport or general aviation, where you ideally want to go to a runway. So here the notion is that you calculate where you can go, make sure your constraints are satisfied, prioritize the runways that you go to, and then build a flight path and land. So we first studied loss of thrust. Just after the data came out for the US Airways plane, we ran that case through our flight planner that had existed for a long time. And this was the Sully's trajectory, where he went up from LaGuardia and ended up in the Hudson River. And what we found is that if the flight planner had activated that you had a choice of all of the runways at LaGuardia and some at Teterboro if you reacted right away. But if you waited even longer than 12 seconds, you couldn't reach any of the runways anymore. This was in the movie Sully, that was also in the NTSB report, but the focus was very different. They were looking at, well, how might we train the crews better? How might we get air traffic control to be faster? What I will point out is the following. If you had Datalink, there would not have been the air traffic control voice delay. It would have been instant, that the system knew this plane lost thrust and needed to go somewhere in an emergency. The second thing is that with this software, which is tractable, verifiable, simple, deterministic code, every plane in the sky, general aviation, unmanned, or Sully, would be able to have an optimal route to a safe landing site in less than a second. All right, so this is looking at where we are with unmanned aircraft systems and emergency landing. A lot of work has been done on sensors and integrating those so that we can pick a local landing site. This simple flow chart is important because it's calling out beyond line of sight needs, which is if your local area isn't safe in an emergency based on your sensor data, then if you can go somewhere else, you should. And what you know about that is from databases, not from onboard sensors. So if you put both together, you're going to have a much safer ability to go and land safely than if you just rely on your sensors and are blind beyond their range. So this is looking at some sensors. And then here, some couple of case studies we did. One is we had a road database for emergency landing where we found road segments and treated them like runways and landed there. Second is that we look at, this is Michigan Stadium, shamelessly put in there, by the way. We looked at occupancy and specifically looking at cell phone data as a measure of occupancy and feeding that into a route planner. This has two purposes. One, it can, in real time, allow you to minimize overflight of populated areas, and two, allow you to select a landing site that has sparse to no population. In the stadium, on the left, this would be a good place for a small UAS to land on non-game days, and on the right, it would be a terrible place to land. All right, I think I have about 1 minute, so I'll have to go really fast. So for the Flight safety assessment and management. This may be the best cartoon to put up here. The idea is that you take a wide array of data to make the best possible decision. In fact, you take as much or more data as the human pilots would have to make a similar decision. So you look at what capabilities the plane has, where it's going, what its dynamics are. You look at the flight plan, and then there's this thing called databases, and make a decision about overriding. So we then collected data in a Markov decision process. We also explored deterministic options, which would be more commensurate with experts in the field building automata-based models, and then separated them into dynamics and control, aircraft health, flight crew characteristics, and then the environment. And within each of those is a wealth of potential to put in information. So with the flight crew, if you have cameras looking at their crew, if you have the history of their actions, you can have a better determination of their state of health. So then the decision itself is simple. Do you let things go, or do you override and have a backup automata or a flight management system take over? Or do you switch control back because the autonomy that you thought was going to work well didn't actually work well? So we did some takeoff case studies. One of the nice things about takeoff is that we've studied all of the accidents that have happened with manned aircraft on runways, and we have a really good understanding of factors that contribute to problems of loss of control. So going right to the end, I'll be happy to share a paper or thesis that has this in it. We did several case studies. This is two of them. This is a case where an Emirates Airlines airplane had a flight crew entering the wrong weight by 100 kilotons, or 100 tons, I guess. Yeah, so they wrote 262 instead of 362. What this caused is that the plane itself didn't actually use its engines at full thrust. It used an optimal engine profile for a weight that was way too light in taking off. So what happened then is that they went past the end of the runway, dragged the tail. They didn't hit anything. They got off the ground, and so nobody died. But that was a data entry error that didn't have to happen. So what we showed is that with this FSAM system, it was able to override before reaching the dangerous, you're going to go off the end of the runway area, and bring the plane to a stop, in which case all they would have had to do is go back, potentially refuel, enter the right weight, and try again. Another example, this is a plane that skidded off the runway due to high crosswind, a continental flight in the United States. One of the nice things, you can get data from the NTSB, the National Transportation Safety Board, has all of the black box data available to download for a lot of accidents that have happened not too long ago. So you can play it back and then look at something like FSAM as to how would it have done if that had actually been the data that was observed. So we've done this with a number of case studies, including this continental plane. And what you find with this plane, and finally, I have some time response plots that make control people really happy, is that if you look at what was done and what could have been done if the automation had been activated, what you find is that the plane with an autopilot could have prevented the pilot-induced oscillations that made the plane leave the runway. All right. Thank you for letting me run a minute or two over.
Thank you so much, Ella Atkins.